A very good evening to everyone once again. I would like to introduce our today's session. Um, Professor Sudershan Rao Nelaturi. Sir is an associate professor of electrical computer engineering at Penn State University, USA. He received his BTech ECE from JNTU in 1981 and ME and PhD from Osmania University in 1983 and 1996, respectively. He was with the Department of EC at University College of Engineering, OU, during 1983 to 1999. He was tenured at Penn State University and has been working in the electrical and computer engineering till date. He has been actively teaching and doing research ever since in the fields of electromagnetics and signal processing, and co-authored over 150 technical articles, including 2 textbooks and 6 solutions manuals. Sir,
Anusha, sorry is there, Nana. Once verify it.
1 second, ma'am. Sudarshan, sir.
Can you hear me now?
Yes, sir. Yes, we can.
Somebody muted. I don't know. Now I have unmuted.
Okay. We can see you and hear you, sir.
Yeah, this is our bedroom, actually.
Okay, sir. Shall I continue?
No, sure.
Sir was recipient of Outstanding Research Award and Council of Fellows Research Award in 2008 from Penn State, Erie, the Barrett College, for his profile publications record. Sudarshan Nelaturi sir has been a fellow of IETE, senior member of IEEE, and was chair of IEEE local chapter for 3 years. And also, sir enjoys Telugu poetry and Carnatic music as his hobbies. Thank you, sir. We are delighted to have you here with for the session. You can take over.
Okay, I have unmuted again. Good evening, everyone. I would like to extend my warm wishes for a happy Teachers' Day. I assume almost all of us are teachers. Today is very special for each one of us. So I want to thank you for welcoming me to this conference. Once again, I want to extend my greetings from Pennsylvania. So the topic for today is, let me share my screen. Give me 1 second. I don't. Where is the button to share? Oh, I see it here. Can you all see the screen, please?
Yes, sir. We can see, sir.
Okay, thank you, ma. Thank you. So the title is, excuse me, the title is Mathematical Methods for Optimal Use of Photovoltaic Energy Sources, Introduction and some Practical Implementations. This topic is not a very new topic, and this very presentation is something I already gave some time back, probably for a different audience. So there's not much new, but the only point is this is very relevant for the title of the conference. You are talking about energy, sustainability, and some mathematical techniques that you come across in this area. So I have selected this topic, and I'll try to do my best. I want to make it as interesting as possible. So I also give you some practical implementations of how you can maximize photovoltaic energy. We all know that there are several alternative energy sources such as photovoltaics, wind energy, tidal energy, and fuel cells, and various types of chemical resources for producing energy and for harnessing and for utilizing for our day-to-day life. So I'm going to focus on the photovoltaics. We all know the solar cells. There's a lot of buzz about the photovoltaic cells, solar energy. Nowadays, there are lots and lots of companies coming up to install solar cells on the rooftop and acquire energy. And also, by doing that, if they return the energy to the grid, they will get energy credits. For this reason, I think photovoltaic energy sources is a very relevant topic. So I'm going to talk about how to maximize the acquisition of solar energy, what we can do, and how to track the maximum power point. And there are truckloads of papers on this maximum power point tracking. You can Google and you will see lots of papers. There are several papers, and many of you must be familiar with many of them, but it's going to be a slight revision of all those things. So let me start with my next slide here. Just a small puzzle for the kids. Of all the four-sided figures of the same perimeter, which figure has the maximum area? Actually, I put the answer there. If somebody has a cell phone, you can just bring the cell phone near the screen and you can read the cell phone. What I mean by cell phone is a mirror. At least the surface of the cell phone can give the reflection. You don't need really a mirror. And the ladies who have their mirrors in their purse, they can also see. The answer is a square. Of all the four-sided figures of the same perimeter, and problems of this sort are called isoperimetric problems. For a rectangle, this is the answer. So for a square, the area is maximum. Okay, let me put it in a slightly different way. The parable of the sower and the pivot technique. There went out a sower to sow in a four-sided patch of soil. He did not like his seeds falling on the wayside because somebody taught him, if you throw the seeds on the wayside, the birds of the air will devour them and the seed is gone and it's a waste. So you don't want to throw the seeds on the wayside, and you want to put them in a prepared soil. And what should be the soil? The soil should have maximum area, and there should be a fence around the soil. So assume that there is an 80 feet fence, and he has to use it and create a shape for the soil in such a way that it occupies maximum area. So he chooses to take a four-sided figure, and if the perimeter has to be 80, the semi-perimeter is 40 feet. In other words, if A is the side, if A is the length and B is the width, A plus B is 40, and our aim is to maximize AB. Suppose this is given to a middle school kid who doesn't even know calculus, and he's asked to make a random guess. So he can start with 35.5. You split 40 into 35.5. The product is 175. Whether it is maximum or not, he doesn't know. He'll try another choice. So instead of 35.5, you take 30 times 10. It is 300, which is higher than 175. What did he do here? He perturbed it. He changed, made a change. Started with some initial guess, but made a change. So that job is called perturbation. And then you observe what is the area that you found. You observe that the area is small. So you're in the right direction. So do the same a little more. Instead of 30, why not we have 25 and 15? It has increased again, 375. One more choice, 20 by 20, the area is 400. So if you are too greedy and if you try to make 21 by 19, the product is 399, and you say, oh, no, this I shouldn't have done this. Let me go back. And you stick to 20 by 20 and keep it there. So this, although it looks very, very rudimentary, there is a fancy name for this technique called perturb and observe technique, PO technique. You may ask why the heck he's talking about a square and a rectangular shape and so on. Very soon I'm going to generalize this. It's not a rectangle with a side. In fact, the letter A here can become an n by n complex matrix. And I will be working with n by n complex matrices, their conjugates, the quadratic form, and like to maximize something there. And I'll apply it to an n-port network. It could be a big solar panel of several individual cells combined, and our job is to maximize the power there. So that's what I have in mind, but I'm starting in a very unassuming way, just for high school kids. So the same problem, if you have to do using mathematics, let's say you want to use calculus for this, any intermediate boy can easily solve this. You can say x plus y is a fixed semi-parameter s, area is xy. You put everything in the form of x and then differentiate equate to 0, solve for x, solve for y, x equal to y. That's a square-shaped area, okay? Here you differentiate here, but without differentiation also, for some simple cases, maximization can be done. And here is one more way of tackling the same problem. If one solution is there, you may ask, why are you looking for other solutions? The idea is every solution has a sequence of steps that you do, and our job is to implement those steps in the form of electronic circuits and some programmable digital systems that can take a certain algorithm and implement them and achieve the objective. So it is better to have as many alternative solutions as possible. And here is one other technique. We know that square of a real number is greater than or equal to 0, whereas square of imaginary numbers would be less than or equal to 0. Of course, 0 is both real and imaginary, you can say. Ignore the 0 there, but all real numbers are positive. Any squares are positive. If x plus y is c, and if you look at the quantity here, x minus c over 2 whole square, this is definitely a positive number. Change the sign, minus times that, and then you expand it and push the c square over 4 to the right. Then you have x times c minus y is less than or equal to c square over 4, or in other words, xy is less than or equal to c square over 4. So this shows the product of xy is always less or equal to c square over 4. At the maximum, you get c square over 4. So the maximum occurs when xy is equal to c square over 4, and equality applies when x equal to c over 2 and that's equal to y. So this is how you get the maximum. Here, I would say this is an idea from real analysis. How are we going to use this for a circuit? Now, all the electrical engineers, they will jump and they can easily solve this problem, but I'm going to put the problem in a geometric way. Here is a simple circuit, a DC source, a source resistance, and a load resistance. A voltage source E is applied. There is a current, let's call it IS. IS is same as IL because it's just a single mesh, single loop here. So if you apply ordinary Ohm's law, you will see that the voltage across the source resistance and the voltage across the load resistance, they are given by current multiplied by the individual resistances. But then there is a constraint here. The Kirchhoff voltage law says some of the voltages must equal, some algebraic sum of the voltages must go to 0, or in other words, voltage rises are equal to voltage falls. So the drop across RS plus drop across RL must equal E. So I'm again going back to the previous problem where sum of two things is fixed. But what is it I want to maximize? Oh, this is what it is. Suppose I represent the drop across RS and drop across RL in the form of a rectangle with the sides ILRS and ILRL. The sum of the sides must be fixed according to Kirchhoff law. But then the area of this rectangle is IL, RS, RL. Here, RS is fixed. Only thing is IL and RL, and those are variables. But you see, this is a quantity that is proportional to PL, which means the area of this rectangle is some quantity that is proportional to load power. So if you maximize the area, you maximize the load power. So what should be the area, or what should be the side of this rectangle in such a way that the area is maximized? So the answer is obviously it should be a square. In other words, the two drops must equal. So the voltage across the source must equal voltage across the load, or the resistance of the load must equal the resistance of the source. How do we implement this in real life? Suppose you have sensors to measure the voltage. If you measure the voltage across these two resistors and create a circuit that compares these two voltages, and whenever they are equal, you say, oh, that's good, that's what I want. The objective is to see that the voltages are equal. And this is called constant voltage technique. Unlike the perturbation technique where you keep changing the sides, maybe you change the resistance, you can anyway see a condition when RL is RS, and here also you can get a condition where VL is VS, then you get maximum power. This is another way of implementing the same thing. Next, I'm going to extend this. You may wonder why he's talking about a freshman problem which any first year engineering student can understand. But the extension of this is what happens when the source is not DC source, but it is AC source. And when the loads are complex loads, and the source also is a complex impedances. So in such a case, how do we change the previous solution? And also if there are n ports, not just one single mesh, but let us say there are n voltage sources and a lot of interconnecting impedances, and there are a big interconnection of loads, then how do you extend this problem? So that's what I would like to address. I mentioned here extensions. The circuit has AC source and AC impedances. It has N-port network. Look at this second bullet. And the third bullet is what happens if the circuit is a distributed circuit, such as a transmission line. And what happens if the circuit has a non-linear source? The previous slide here, it talks about ordinary DC source and the resistors. They obey plain Ohm's law, which is a linear relationship. But suppose instead of RS, let us say I have a diode there. How do you apply maximum power transfer theorem in case of nonlinear loads? That's an interesting question, which ordinary freshmen or sophomore students, first year or second year engineering students, they don't come across nonlinear loads. The nonlinear solutions are normally taught in the graduate school, and there is a different solution for that, which I'm going to show later on. Now, if you go to the AC source, I have actually slightly complicated that. If RL and XL are the real and imaginary parts of the load impedance, and the power at the load is given by this expression which you see on the top. So we want to maximize this. So you can differentiate with respect to XL, differentiate with respect to RL, equate to 0, and then you can also look at the SCN here. I'm assuming that it's a general two-variable maximization problem. So you look at the SCN and find the eigenvalues. And in order to maximize, you have the contours of the objective function PL I just showed here. And I also, actually the contours are constant lambda 2 values. Lambda 1 and lambda 2 are eigenvalues. And I plotted all the contours there. And I find that the lambda 2 contours inside this shaded circle, both the eigenvalues are negative. One eigenvalue is anyway negative with a minus sign here. There is a plus sign also. This is basically a quadratic. You get two eigenvalues. So we want both to be negative, then H is negative definite. So that's what you study in optimization of two or more variable functions. So you can do that, and it's plain and simple, but point is, how do we implement using a programmable circuit? That's the question. So we look at another slide here. And in this, I'm seeing, of course, I showed the boxes, ZL and ZL, ZS and ZL. Those are not simple boxes. They are N-port networks. Even this E here is not a single source. I just modeled it as one simple circle with plus minus polarities. But actually, this is a Thevenin equivalent of a big N-port network where the voltages are n element column vectors, and the impedances are n by n complex matrices. And the load that is attached to this is also n by n complex matrix. So if you want to maximize the power, look at this quadratic form here. The PL, the load power, is given by IL Hermitian and the real part of ZL and then IL. So if you calculate this, you get the power. And I'm going to expand it in this way using the relation between the voltage column vector, current column vector, and the impedance matrix. So this is what you get. And now I'm taking gradient PL with respect to ZL conjugate. In case of complex valued functions, suppose a function is it is dependent on a complex variable z and complex variable z conjugate, then you'll have to differentiate with respect to complex variables, but z conjugate is not analytic. Whenever a function with z conjugate is there, you can't differentiate that because it doesn't satisfy Cauchy-Riemann equations. So the way you do that is you take the formal derivative, treat ZL as a constant and differentiate with respect to ZL conjugate, and then equate to 0, then you will solve for ZL. That's called formal derivative. And here I am differentiating with respect to matrix, and this is something undergrad students don't come across. You only differentiate with respect to a variable x, or if you have a bunch of variables, you do partial derivatives. But here, differentiating a real function with respect to matrix requires some set of formulas. You look up those formulas and you expand and somehow you write, you get all this lengthy thing. And if you equate, ultimately what you get is what you expect here. ZL is ZS conjugate. The matrix, the n-port impedance matrix of the load must be complex conjugate of the n by n matrix of the source. That's back to the same result that many of the electrical engineers are very familiar with. But the derivation only looks a little bit more mathematical. Other than that, the spirit is just the same. Now, these are a couple of techniques to maximize something, but there is another situation here. Look at this. I am extending this to a nonlinear source with a nonlinear load, nonlinear resistance, which means in this circuit which I'm showing, Ohm's law doesn't work. Here I have put RS. This could be a diode, or it could be any other semiconductor device, or some chemical system, or whatever it is, where the linear laws do not work. But if there are nonlinear relationships, how do we maximize the power? So you take the expression for PL, it is product of VLIL. If you differentiate using the UV formula, differentiate with respect to VL, you get IL here, differentiate the other thing, then you get VL times DIL over DVL. This is just the product rule. Now, the derivative D over DVL can be written as minus DIS over VS because the voltages here and here, they are constrained by the Kirchhoff laws. Therefore, you get a minus sign here. And if you equate, you will find something interesting. And this is the condition for maximum power in case of nonlinear loads. And that condition says GL, which is the ratio of IL to VL, is the electrical static conductance or DC conductance, whereas that is equal to DIS over DVS, that is the dynamic conductance of the source impedance. The source side, there is AC conductance, and the load side, there is DC conductance. If these are matched, then you get maximum power. You are certain that at the load you get maximum power, because this whole thing came from this simple equation. You differentiate with respect to VL and then equate to 0. And this technique is called incremental conductance technique, IC technique. What you do is you use some transducers or sensors and make an arrangement that would measure the incremental conductance, which is the AC conductance of the load of the source, and also measures the conductance of the load and maintains equality between them. If you can create a circuit that does this, then you get maximum power. And from any photovoltaic source, you can get maximum power because photovoltaic sources are highly nonlinear. So this is one idea here. And here I am showing another graph. Suppose you plot a graph for PL with respect to VL, you get a parabolic curve like this. There is a clear-cut maximum. To the left, when GL is greater than GS, this is how power varies. When GL is less than GS also, power is less than the maximum. It falls down like this. Only if this capital GL is equal to little gs, here you get maximum power. So you can achieve maximum power by incremental conductance technique. That's this method. Then let's use, of course, the same circuit. Here I used the Thevenin model. You can actually work with Norton model using current sources. You get the same result even in case of a Norton model. The final point is the load conductance must equal the dynamic source conductance. That method which maintains this equality is called incremental conductance method. So we have seen PO, which is perturb and observe, and we have seen the incremental conductance method. And there may be some other methods also. So let me go over to one more method. And in order to do that, I would like to show one figure here. Looks like somebody gave a text. Let me see. What is this here? Chart? Did anyone? Is there any question, please, which I'm not able to read? Does anyone have any question? I think you're all muted. Okay. Okay, here is a graph that shows how load voltage and load current changes in a simple DC source, DC resistance and DC load. I have two straight lines. This blue line, normally it is called load line in case of electronic circuits textbooks, but I would like to call it a source line instead of load line. On the other hand, the Ohm's law that the load obeys is this, this yellow line. This I would like to call load line. The intersection of these two is this point. If that point is called Q point or quiescent point, that point tells you what is the drop across the load and what is the drop across source. This length is drop across load, and this length is drop across source. And if you combine both, that's the total source voltage E. What this shows is, if you move the Q point anywhere on this line, the drops here, how the source voltage is split between source and the load, keeps changing. We want this to be exactly in the middle so that maximum power is obtained. And that is a constant voltage technique, which normally people use. That's also a valid technique, okay? I'm giving some more explanation here. Take the same graph. I draw a rectangle here, this green rectangle, and this is a yellow rectangle. This green rectangle is proportional to the power dissipated in the load, and the yellow rectangle is proportional to the power in the source resistance. Both the powers combined is the total power, right? So I want to maximize, so that happens only when Q is exactly in the middle. In real life, there may be plus or minus 5% of error, but if you can maintain these constant voltages, the technique that you follow is called constant voltage method, okay? And then I'm going to another method, which I developed some years back and published in Journal of Power Sources. Many of us know the Lagrange method that's used for optimization. I found that nobody used it. So why not I use Lagrange method to maximize? And for that, there is a small puzzle here. I call it the parable of the milkmaid. There's a milkmaid, and that lady goes from A and she has to go to B. She starts with a milk can at A, and there is a cow at B. She wants to go and milk the cow. She can go straight from A to B, but she would like to wash the can or probably carry a little water. There is a river here. The green curve shows the river. So she wants to go to the shore of the river, wash the can, and come to the cow. So at some point, she has to go to the river. So she can go like this and go to the top and then come, or she can go all the way there and then come. There are several alternatives. Of all these, which one is the shortest path? This one was solved long, long back. Lagrange gave these ideas. It's called Lagrange method. All you do is draw confocal ellipses with A and B as foci and draw several ellipses like this, but there is one particular ellipse that is tangential to the given curve. All other ellipses cut at 2 points. Some ellipses don't cut at all. So if you look at the smaller ellipses, they don't touch the river at all. So if you go to any other ellipses that cut at 2 places, you won't get the a minimum shortest path. Here, of course, the problem is to minimize this. So anyway, here, if you go from A to B like this, where this is tangential, then you get the optimal value. So take this idea and put it in mathematical form. In case of ordinary DC circuit, if you see, the river here is given by these contours. Instead of the elliptical contours, I have the hyperbolic contours, which are constant power side. So on these hyperbolas, VL, IL is constant. You can have different hyperbolas, and this source line is tangential to only one of them, and the point of tangency is the point where you get maximum power in this DC circuit. You don't need this kind of messy or more mathematical ideas, because a simple calculus problem, why are you taking it there? My idea is to extend this when these two becomes nonlinear and time varying, and there are several other constraints also. Then you have to use these methods and look for alternative solutions. So if you want maximum, the middle red dot is the only maximum for this, where the constant power curve is tangential to this source line. Okay, this is also called load line in electronic devices, but I'm calling it as source line. So let me put that in mathematical notation. What Lagrange does is, you take the objective function that you want to maximize, which is the product of voltage and current, subject to the condition here. This is the constraint. The second equation is the constraint. And you choose the Lagrangian here by selecting some arbitrary constant called lambda. You call it multiplier. It's Lagrange multiplier. So you take this new function and then differentiate with respect to lambda, VL, IL, and equate to 0. You get a bunch of equations. And if you solve them simultaneously, all the three together, then you get the solution. And this is such a simple thing. The solution is back to RL equal to RS. That's very straightforward for DC circuit. But what happens if you have photovoltaics? That's the main point here. What are these photovoltaics? They are renewable energy sources. They convert solar energy to electric energy. And advantages are solar energy is clean, no toxic, no smell, no fumes, nothing. And it's high power densities there, and it's free coming from the sun. God has made the sun. We have free energy from the sun. And it is quiet. There are no moving parts. If you use a generator or whenever there is power cut, some people use generators, and you get disgusted to hear the dug, 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 dug. That sound is extremely noisy and very disgusting. So sun doesn't cause any sounds, so it's quiet. And energy management strategies in some combat. Pardon? It's not very clear, but it's okay. Thank you so much. There are some combat vehicles used in military operations. You should not have the batteries made of the chemical sources. They may produce some signals which can be easily detected. So in combat vehicles for silent watch operations, solar cells are better. And you talk about sustainability, easy maintenance, and low operating costs. Only initial capital is involved, but then afterwards there's nothing to do. And the solar power is not a power theft. If you take solar energy from the sun, it's nobody's property, so don't call it theft. So consumers actually, they can take it, and if you put it back to the grid, you get energy credit. Has exceeded 2 terawatts, and 2030 is expected to reach 8 terawatts. And various countries solar energy. So what are the materials used to make solar? You can read any textbook. The solar panel is made of some crystalline silicon, mono or polysilicon, as well as non-crystalline, cadmium telluride, copper, indium, gallium selenide, sulfide. These are all some materials that are used in photovoltaic cells. And what's important for electrical engineers is the equivalent circuit here for the solar cell, which involves a constant current source, resistor, a shunt resistor, a series resistor, and a diode here. All of it together is not a linear circuit. And the equation between the solar voltage at the cell and the current is somewhat nonlinear. I'm going to show it now. And the curve that I showed earlier, which was a straight line, is no longer a straight line. It looks like this, is flat here and then falls down. And if you take the product of the voltage and current, the power curve looks like this. And the maximum power comes here. And this occurs at the knee of the voltage current characteristics. So if you are using a solar cell, your aim is to get to this knee and stick there, be there, don't move from there. Thereby you get maximum power all the time. And the equations that I mentioned are similar here. The power equation is the product of voltage and current. And the others, here you have a nonlinear equation. Now, if you create the Lagrange optimization problem, you have a lambda, which is Lagrange multiplier, and this is the thing that you should work with. So if you work with that, and graphically I'm showing the constant power curves, they are these hyperbolas. One such hyperbola is tangential to this. That is the goal. You want to fit there. That is the maximum power point. Okay. For this, just like I showed earlier, you differentiate the objective function where lambda is the multiplier, eliminate that, you get pair of nonlinear equations. You can solve this using any numerical technique, such as a contraction mapping, or the Gauss-Seidel method, iteration method. Iteratively, you can do that. When you do, you get maximum power. And that happens when you plot these two functions. I call it as chi1 and chi2. So those two, if you plot, they intersect there. That is the maximum power, MPP here. Look at that. And if you start with a random guess, you can use an iterative technique to go there. And this is the cobweb diagram that shows how iteration after iteration power changes. Okay. If you plot the constant power curves and the VI characteristics for various solar incidences, you get this set of curves here. In all these curves, the maximum of power point is this, where it touches at the knee. That's what you should do. So now the question is, if the solar intensity changes, you'll have to move this point accordingly in order to achieve maximum power. And likewise, if temperature is changing, then also this the VI characteristics keep changing, and the point of tangency keeps changing like this. So you need to provide an arrangement to track it. Okay. So in case of the DC circuit, which I showed earlier, I said if you change the load resistance, the straight line that obeys the Ohm's law and that is shown here keeps moving up and down. And the only way you can optimize is to see that it goes through this midpoint where the voltages are equal between the source and the load. If you move on this side or on that side, you will get suboptimal solutions. And for this, you can do one thing. Suppose you have a source here and you have a load there. If the load is varying, or from the source side there are variations, in between the two, if you use a DC-DC converter, this will change the impedance offered by the load in this way. Suppose at this point, if you see the looking impedance, you make sure that the looking impedance in the right direction here at this location where the cursor I'm putting must equal the impedance of the source, then you get maximum power. For this, there are 3 suggestions given by people. You can have a buck converter or a boost converter or a buck boost converter. In any case, you can fix the maximum power point and keep it there. For these 3 converters, there are some formulas which you can find in any power electronics textbooks. There is a switching device there, a MOSFET or something of that sort, where you can change the duty cycle. Delta is the duty cycle for all the 3 converters. By changing the delta, you can change the input resistance offered by these converters. Those formulas are there. If you can meddle with this, it is possible to have maximum power. And I'm giving you some circuits. This is a buck converter. Those who studied power electronics, they are very familiar with the buck converter circuit, the boost converter circuit, the buck boost converter circuit, and so on. And the formulas are there. For all the 3, of course, I separated those formulas, which you can find in any textbook. And this is the scheme that I proposed some time back. It's the scheme called Lagrange MPP tracker. What we do is, here you have a PV module and here you have a load. So you use this DC converter and decide on the duty ratio. And how you do that is to solve the equations I showed earlier. And by solving those equations, and you can mess with the duty cycle. For this, you need an LU table. What this table means is the values of chi functions that I showed, you put there in a tabular form and look up the table and get it. Don't ever try to calculate complicated nonlinear equations because that will consume a lot of computational power and it's a nuisance. Instead, if you have a lookup table for all the complicated quantities, you can just access for a given voltage and current, just take the value and then feed it. So that's how you work with that and then create it. And I did that using a software called PSIM. It's a simulation. So here is a simple schematic, and you have a PV panel here, and this is all the circuit, and there is a load resistance. I assumed two different conditions: when the solar irradiance is changing, or when the temperature is changing, or the load resistance is changing. You can see how maximum power is tracked. And the solar panel that I used here is SolarX MSX60. That's pretty old model, but it's a useful thing. And I'll show you the graphs, the way these times are calculated and found, and that's also there in this slide here. We don't have enough time, so I'll just pass and show the graphs here. Look at how the power is tracked when the load resistance is made to change. You can see how that red line there is the maximum allowable power. And when there is a change, in no time, you just go back to that. Here, you see how the voltage is changing because of change in the load resistance, and current is changing like this. Although the current is changing and the voltage is changing, the power that I have is so adjusted to reach the maximum very quickly using this Lagrange MPP algorithm. And it works well compared to other techniques. It's really beautiful. Those who are interested, I can give the paper to you, or you can just Google my name. You will see it in Journal of Power Sources. There is one more graph here where the solar irradiance is changing, and in spite of that, you reach the maximum that is defined, and that's how it works. So in conclusion, we have revisited the maximum power transfer theorem, and I gave the importance of this, advantages of photovoltaics, and implementation of maximum power point algorithm using DC-DC converters. Basically, this converter changes the looking impedance. The impedance seen in this direction towards the load is somehow equated to the impedance seen on the other side. And that's done using the duty ratio delta. By changing that, you can do that. And we introduced the Lagrange method. So this is what I discussed in this short time. I think I exceeded. So if you have any questions, I'm open for the questions. I'll take your advice or anything to improve this talk, or anything you want me to talk, I can answer all the questions. Okay. Any questions, please?
Hello.
Hello, sir. Hello.
Sir, first of all, I would like to say thanks to you. The
You're
thing
welcome,
how
sir.
you have,
Thank you for
yeah,
inviting me.
how you have started with the mathematics and the basic things, and from that
Uh,
you have developed the respective electrical problem. I am really
uh.
very impressed, and I am really very happy to attend this session, sir.
Oh, thank you, sir. Thank you for your encouragement.
So I just want to say, sir, is it possible to have this PPT, sir?
Why not, sir? I will send it to Dr. Vasundhara madam, and you can take from her. She will distribute to anybody. I can email her in few minutes.
Okay, sir. Thank you, sir. Thank you,
If
and very nice
if you
session.
want, I can send a couple of my papers. I wrote one paper on purely maximum power transfer theorem. In dozen
Okay.
different ways, I proved it and extend to N-port network. There is a
So,
theorem called Pythagoras theorem. You know Pythagoras theorem? Any high school kid
yeah,
knows that. There is
yes, sir.
only one
Everyone.
way that is taught in the textbooks, or in some textbooks, 2 or 3 different ways will be there. But if you open internet and look up a website called Cut the Knot website, there are more than 120 or maybe more. I have to have to look today. As on today, there may be several ways of proving Pythagoras. I used to think why so many methods are given just for the single Pythagoras. The idea is to have some kind of brainstorming and to see alternatives, because if one alternative doesn't work, you can go for another. So the maximum power transfer theorem I proved in dozen different ways in a small educational journal paper. And also I published this in Journal of Power Sources, where I used the Lagrange technique and showed how you can get the maximum power. I'll send it that also, sir. I'll send to the Vasundhara madam.
Thank you, sir. Thank you, sir.
You're welcome. Any other questions, please? I'm happy to look at all the young faces, upcoming budding engineers, budding professors. So you can take up any research problem in energy related area and do your PhDs if you don't have PhD, or if you already did PhD, you can guide others.
Any questions? I would like to take this opportunity to extend our heartfelt thanks to Professor Sudershan sir for such a rich and insightful session. Your talk reminded us that behind every climate model, whatever it is, there lies the language of mathematics, the equations, data, and logic that helps us to understand the complex systems shaping our world. Thank you very much, sir, once again, and happy Teachers' Day to you.
Oh, happy Teachers' Day, and I'd like to thank you for giving me this opportunity. Some people say don't put too much of mathematics, make it more easier, but somehow I differ. The gathering being mathematics community and also electrical engineers, math is a universal language and math is a medicine of the mind, I would say. If I use math and continue in math, my Alzheimer's will be delayed. I'll remain active. If I do even Pythagoras theorem 1000 ways, I think I'll be very active. So I encourage all the faculty to go back and collect all your math books and continue the work. Okay, use it and implement it. Let the electrical engineers implement. Let the mathematicians provide the math necessary for that. So I would like to thank for giving me this opportunity. Thank you, Dr. Vasundhara madam, and many others whom I don't know. I may know some of you, but anyway, I want to thank you once again. Have a happy Teachers' Day and enjoy the rest of your time. Thank you.
Thank you, sir. Thank you once again for your valuable time. We'll end the session for today, and we'll be
Anusha,
guiding.
Anusha, 1 minute. Anusha,
Yeah.
1 minute. Please announce it tomorrow from 2 to 8.
Okay.
Whatever I posted in our Max group.
Okay, ma'am.
Read out it.
Yes, definitely. Just give me a minute, ma'am. I'm going to just. So tomorrow we are having 3 sessions. That is, it's starting from 2 p.m. and we are having a session on from Mr. P. Radhakrishna Murthy Garu. And also 3:30 to 5 p.m. we are having applications of data science and sustainable energy by Dr. Abhilash Pochiraju sir. And coming to 5 p.m. to 6:30 p.m. we are having sustainable energy sources in India session by Professor V.V. Basavarao Garu, and he's a vice chancellor from your Rayalaseema University, Kurnool, Andhra Pradesh. And from 6:30 p.m. to 7:30 p.m. there is an online test, and also will provide the feedback form to you to fill it up. And 7:30 p.m. to 8 p.m. we have a valedictory session. I hope I am clear with all the details. Tomorrow we'll see you at 2 p.m. Thank you, everyone.
Thank you. Thank you, everyone. Appreciate.
Thank you, Sudarshan sir. Thank you very
Thanks,
much.
Amma.
Happy
Thanks.
Teachers'
God
Day.
bless. God bless you.
Thank you, participants. Tomorrow, once again, we will meet you at 2 p.m.
Oh.
Thank you, one and all.
Thank you. Bye-bye.